Hello everyone. Today we are going to cover section 6.4, differential equations with discontinuously forcing functions. My cat is telling you hello. And we are going to give several very simple examples of how to solve differential equations using step functions. I'm going to just consider examples. There's going to be no special theory here. Okay. So we start with a simple differential equation. It's not even a second order differential equation. Give me a second. So it's very strange. I don't like this thickness. Let's consider a differential equation which looks like this. 2y prime minus y equals u3 of t. Very simple one. It's initial value problem, y of 0 equals to 0. First order equation with right side which is equal to a step function which makes a jump at point 3. So u3 of t has a jump discontinuity. At t equals 3. And now how can we deal with this? Because so far all g of t are right side were continuous, right? Well, we're going to do Laplace transform of equation first, right? Apply Laplace transform. And we remember that derivative is going to give us what? Well, the coefficient 2, and then it's going to be as Laplace transform of y minus, we're still transforming the derivative, y of 0. And Laplace transform of y is just Laplace transform of y, right? We use a special formula for a derivative. On the right side, what we have, we'll need Laplace transform of u3 of t, right? So I'm going to combine the left side together and combine the right side together. So y of 0 equals to 0. So this one is equal to 0. We don't need to worry about it. We're just going to have Laplace transform of y multiplied by 2s minus 1. I'm taking this one outside of parentheses and the one outside of parentheses. Here, Laplace transform of u3 of t. You probably remember the formula. That's e to the power of negative 3s divided over s. That's the first formula we started last section 6.3, right? We found Laplace transform of step function. And here c equals 3, right? Well, what are we going to have next? Well, next we solve for actual Laplace transform, right? And then kind of find inverse. Very simple way to solve it. So I'm going to express Laplace transform isolated on the left side, and the right side is going to have e to the power of negative 3s divided over s and 2s minus 1. Well, we remember that this e to the power of negative 3s is a shift. So we don't need to deal with it, but the fraction in the no, like the fraction which is multiplying by this expression is going to be like interesting. We can decompose it. I'm going to continue over here just to not copy everything again. So I'm going to move e to the power of negative 3s in front and decompose the fraction 1 over s, 2s minus 1, into two fractions, a over s plus b over 2s minus 1. Find the coefficients and kind of let me do it. I'm going to do it somewhere here, okay? So, so if I represent this fraction like 1. So I'm not representing just denominator, it's a whole fraction. It's 1 over this denominator, right? Let me make 1 nicer. Okay, so bring it to common denominator. What is going to be? It's going to be a 2s minus 1 plus bs and divided over s 2s minus 1, right? Now I'm going to collect coefficients in front of s, which is like 2a and b. And because we don't have any s here, it's going to be equal to 0. And coefficients in front of like s to the power of 0, which is like free term, is going to be a multiplied by -1, which is minus a. And it's supposed to be equal to what? Well, it's supposed to be equal to 1, from where we can make a conclusion that a equals -1 and b equals minus 2a, which is going to be just 2. Sorry, 2 not supposed to jump like this. Let me fix it and write it down minus 2a. I'm solving the first equation for b and equals 2. So I'm going to write it down in this parenthesis, kind of continue it, right? So you have minus 1 over s plus 2 over 2s minus 1. What is next? Well, next I'll need to find Laplace inverse, right? To find y, it's actually Laplace inverse. Y is going to be Laplace inverse of e to the power of -3s, -1 over s plus, I'm going to divide numerator and denominator by 2 over here. 1 over s minus 1 over 2. Well, you probably are going to guess why I'm doing this, just because my standards expression doesn't have any coefficient in front of x, right? Well, now what I'm going to do, I'm going to use my rule that this one is just shifted Laplace inverse of this expression, right? So I'm going to write down that this is u3 of t, why it's 3, because it's -3 here, right? And expression, Laplace inverse of each of these two functions is -1, first function, right? And plus e to the power of 1 over 2. 1 over 2 is this one, right? And here I'm supposed to write down t, but I remember that it's supposed to be a shifted one. So shifted one is going to be t minus 3. Why didn't I shift this one minus 1? Well, we can shift minus 1, but if you have a constant -1, you shift it 3 units to the left, 3 units to the right, it's still going to be the same constant. So that's going to be our final answer. And this one, we have this -3 because it's shifted. You see, very nice way to solve discontinuous equations. And next example. Another example, I'm going to use window function p12, and I'm going to represent it as u1t minus u2t. Okay. I'm going to set up initial value problem, and it's going to be second derivative of y minus y equals u1 of t minus u2 of t. Initial conditions, y of 0 equals to 0 and y prime of 0 equals to 0. Just to make everything easier, okay? So I'm going to start with Laplace transform. So Laplace transform of this expression is s squared, second derivative, right? Laplace transform of y minus s by y of 0 minus y prime of 0 minus Laplace transform of y, right? This one. And equals Laplace transform of u1 minus Laplace transform of u2. Okay? So what we have over here, well, this one is equal to 0, this one is equal to 0, so we can kind of concentrate Laplace transform here and multiply it by s squared minus 1. And on this side, what do we have? e to the power of negative 1s over s minus e to the power of negative 2s over s. Well, we're almost done. We just need to modify a little bit our expression. So I'm going to solve it for Laplace transform, isolate Laplace transform of y, which is going to be e to the power of negative s minus e to the power of negative 2s divided. Denominator is same here, so I'm going to keep it over here, and then I'm going to have s squared minus 1, which is like the factor of Laplace transform. Here I'm moving it to the right side. Well, looks like I put a minus. Whenever I put a dot, it doesn't look like a dot, looks like a minus. I'm sorry. That's of multiplication. Okay, now what I'll need to do, I'm going to start with decomposition of the fraction. I know these exponents are going to give me shift, so I'm going to decompose fraction 1 over s minus 1, s plus 1. Supposed to be parentheses, I forgot about parentheses. That's gonna look very nice. Well, I decomposed s squared minus 1 into two factors. So let me write it down. That's a over s plus b over s minus 1 plus c over s plus 1, right? Undetermined coefficients. I'll bring it to common denominator, and I'm going to have 1 from the right side equals a minus 1 s plus 1 plus b s plus 1 s plus c s minus 1. Just brought to common denominator and make numerators equal. Right, now I'm going to set up, when you have three terms, good three factors or three kind of fractions, a good idea to use this, like, not solve system of equations, but use substitution method. So I'm going to put s equals 0 and calculate left and right side of my expression. Well, on the left side, I have 1. On the right side, if I set up s equals to 0, I'm going to kill this term and this term. And only term which is left is this. And here I'm going to have 0 minus 1, 0 plus 1, which is going to give me minus 1. And that's going to be minus a. So I already have one coefficient. A equals minus 1. Now I'm going to set up s, what? S equals to 1. And plug in 1. Again, left side does not depend on s, so it's still going to be 1. When I plug in 1 here, it's going to kill or make 0 this term. And if I plug in 1 here, term with c is going to disappear. The only term is going to be left with term with b. So I have b and s plus 1, which is 1 plus 1 is 2, and multiplied by 1, right? From where I can calculate that b equals 1 over 2, and the last one, s equals negative 1, is going to kill term a, and that's going to kill term b. So the only term left is c. So I'm going to have 1 equals negative 1 by c, negative 1 instead of s, and minus 1 minus 1 minus 2 multiplied by negative 2. Basically, these minuses are going to cancel, and my c is going to be 1 over 2 as well, right? Now, what should I do? Well, guys, I'm not going to do multiple steps at the same time. I'm going to write down everything as a fraction and then kind of show you what is going to happen with it. So now my decomposed fraction is going to look like this. Minus 1 over s plus 1 over 2, 1 over s minus 1 plus 1 over 2, 1 over s plus 1, right? That's decomposed fraction. What else do we have? Well, besides decomposed fraction, we have the factor e to the power of negative s minus e to the power of negative 2s. And this is Laplace transform of y, right? So now we'll need to find inverse of this long expression. Well, I don't think that everything is going to fit into this page, so I'm going to move to the next one. But on the other hand, I don't want to kind of lose the view of expression. I think what I'm going to do, guys, I'm going to just maybe use a different color and do modifications. So what is this? This is u of 1, right? What is this? This is u of 2. So basically, each of them is going to shift this function, the whole thing, to a different number, right? I'm going to start with shift 1 unit. So, well, I'll need to write down inverses first, right? I'm going to write down inverse. So inverse over here is 1, right? What is inverse here? Inverse over here is e to the power of t, just expression, not 1/2. 1/2 is going to stay. And inverse over here is e to the power of negative t, right? Now I'm going to combine the coefficients. So what is going to be my y? My y, well, what I'm doing right now, guys, I'm taking inverse of this big expression to get y. Actually, I'm going to write it down, that y equals to the inverse of this expression. So what I'm going to have, u1, and I have to shift all these functions into 1 unit, right? Well, because it's just -1, I'm not going to do any shift over here. But for this one, I'm going to write down that's 1 over 2 e to the power of t minus 1, shift by 1 unit, and 1 over 2 e to the power of negative t. I'm going to write down +1 because if we shift it -1, it's going to be minus and minus plus, right? Okay. Now, the second one. Well, I think I'm not gonna fit it here. Let me move this panel so I can write down here. Plus u2, right? This second one. Oh, why it's plus? It's supposed to be minus, right? Let me put minus. Minus. And basically the very same functions, but shifted 2 units. So still -1. Why don't we shift -1? Again, we don't shift -1 because it's a constant. Constants are not shifted. You can shift them, of course, but they're not going to change. 1 over 2 e to the power of t minus 2 plus 1 over 2 e to the power of negative t. And if you do -2 after minus, you are going to get +2. That's going to be the final answer. Okay. I don't know. Maybe I should write down the formulas which I used because maybe it's not very clear. So which formulas I used? I used the formulas that inverse of 1 over s is 1. I also used the fact that inverse of 1 over s minus 1 is e to the power of t. And I use the fact that inverse of 1 s plus 1 is e to the power of negative t. And of course, I use my theorem, which I proved in the previous section 6.3, that like when we multiply by exponential factor number s, like minus cs, it's actually shifting the whole function by c units and multiplying it by a step function. Okay. Looks like I'm done with this question. We're not gonna go further. Normally, guys, no one is doing like just very simple functions, which are like step functions or window functions. Normally, people are multiplying something by step function. So in a general equation, it's not going to be u of 1 minus u of 2. This is like equation for the school, but normally it's going to be probably a portion of sine multiplied by this expression, or cosine or exponential function, maybe several of them, like sine and then cosine and maybe exponential function mixed together. But it's going to make solution super long. So you understand, the idea is that we normally use these ones to cut something of a real function, like, for example, sine of t. And that's going to give you a portion of sine, not the sine which goes from negative infinity to positive infinity, but sine which goes from 1 to 2. The only little piece of sine. So you turn on sine at point t equals 1, so at 1 second, and turn it off at 2 seconds. What is going to be a solution? And we remember superposition principle. When you solve differential equation, you can solve separate right parts separately and then add them together. So like if you have more different functions over here, like not only sine but cosine or whatever, any other different function, you can solve separately each of them and add them together. Okay, that's all about section 6.4. And I think we are done with Laplace transforms. We're not going to cover everything. Unfortunately, we don't have time for this. Okay, let me... cannot deal with my recordings.